One final note on Kas and Kbs is how to convert between them, which is something that we will commonly have to do. So, for example, if you go to your textbook, Appendix G in your textbook has a list of Ka and Kb, well, only Ka values, I should say pKa values, for many common acids and bases. And these are only given as pKa values, right? So if we need to find a Kb value, we need to know how to convert between these two. And so this is a relationship between a conjugate acid conjugate base pair, right? So if we have HA, dissociating to H plus A minus, we can also write A minus plus H2O acting as a base, forming HA plus OH minus, right? So we have these two reactions that are both happening. And we need to figure out what's the relationship between this will have its own Ka value and this will have its Kb value. And is there a relationship between these two? If we add these equations together, we can see that the A minuses will cancel, the HAs will cancel, and lo and behold, we get H2O in equilibrium with H plus OH minus. Well, that's equal to Kw, right? So that's our autoprotolysis of water. And we know when we add equations together, we can multiply their K values. So that means that for a conjugate acid-base pair, the Ka times Kb values is equal to the Kw value. Another alternative way to write this is that pKw, which is equal to 14, is equal to, not plus here, is equal to pKa plus pKb. Similar to the relationship between pH and pOH. If we take the p value of everything here. So this gives us a way to convert. If we know the Ka value, which is usually what's listed in tables, we can find the Kb value for the conjugate base if we need it as well. One other thing to note, for example, and this will be more relevant for the next chapter, but if we have a polyprotic species, more than one proton that can be lost, the form that will be shown in Appendix G is the fully protonated form. So writing a specific one here. So this is, all right, go away. This is anthranylic acid. All right, and each of these has its own pKa value. So we have pKa for the carboxylic acid group is 2.08, and for the NH3 group is 4.96. Right, and if you go and look it up, you'll see each of these individual values here. If you want, it'll specify which hydrogen is being lost for each of these. So right, so for example, this one will say CO2H or NH3 here, for example. So that's the way, at least in your textbook, it shows these. It's always the fully protonated form, and it'll specify which proton is being lost for a specific pKa value that's listed. And then if we need the base, we use this relationship that we've just gone over to convert between Ka and Kb.